So what it means is that the Earth's actually turning itself inside out.
That makes Earth unique.
It just continually recycles its surface into the interior.
Oh, interesting.
And forms new parts of the plate. So if you strip off the oceans, you see something quite different. You see these sort of systematic mid-ocean ridges, which are mountain belts right in the middle of the oceans, great trenches. You see all this structure, but in terms of geology, it's kind of like one thing. You just see the bare plates. And the plates are these big blocks of the Earth's crust. Plate tectonics is something that came out of the fact that we suddenly were able to observe beneath the oceans after the one of the really big observations was the connection between the formation of the plates and reversals in the Earth's magnetic field. So we don't know that a big planet that suddenly starts plate tectonics and turning itself inside out might actually get all of its heat out suddenly and then run out early. So it's all very unclear. What we know the end state, eventually it runs out of heat and everything must stop. So it's true for the Earth and it's true for Mars, it's true for Venus. So eventually they'll run out of radioactivity to generate any more heat and they will eventually run down to nothing.
Right. Louis, thank you for joining. It's a real pleasure.
Yeah, pleasure for me too.
So you're a geophysicist. You study geodynamics. For those who are not familiar, could you describe what geophysics and geodynamics is to start with, and then we can slowly get into the conversation.
Absolutely. So, as a geophysicist, geodynamicist, I think about the whole Earth as a planet. I usually think on a very long time scale, so I think about the Earth from its original formation through to the present day, 4 billion years worth of, or more than 4 billion years worth of evolution, long story. Mm-hmm. And I'm interested in the physical processes that go into making that story happen. So I'm interested in the way that, for example, plate tectonics works. Plate tectonics is the big story, right, about how the Earth operates. And I think about the processes that are responsible for plate tectonics, how it could have turned out differently, how it relates to different planets, how other planets in the solar system don't have plate tectonics and the Earth does. Why is that? What's different?
Yeah.
Why, what's so interesting about that? So that's kind of my sort of big, broad brush description of what geodynamics is about.
Right. And is that the entire field as well, or are there other pieces that are part of it?
Well, it's a very interdisciplinary science, and one of the reasons for that is it's sort of geophysics and geology in general is really quite like astronomy. You can't do experiments, you just observe what happened, and a lot of the time you're looking back and forth to different times and saying this thing that I see now must have been like that thing that I can see has happened before, and try and study sort of as a forensic science, rather than as sort of a lab-based science where you sort of set up an experiment, you have a control. And what that means is that actually you have to be quite broad about that. You have to bring in lines of evidence that you wouldn't otherwise necessarily. You wouldn't set up in an experiment. You would, but they're there. There's still things that you have to take account of. So you might be interested in trying to understand how plate tectonics works. So you've got to understand how did the rocks get how they are, and to understand that, people have to go out into the field. You have to do some kind of imaging. Could be satellite imaging, could be seismometers, creating images of the subsurface. All this stuff goes into the mix.
Right.
So you find like the stories are very rambling. They amble from place to place and from part to part, and then you end up with something that is convincing.
Right.
But there's lots of little sort of side paths along the way that you need to go down and cover before you really understand the whole story,
the bigger picture. Yeah. And you mentioned that the field and yourselves, you study apart from Earth, other planets in the solar system and beyond. How much is the difference in the way the other planets compared to Earth itself is? And let's start with the difference, and then we'll go to history of Earth, and then come to its layers and the story from there.
Sure, why not? Right, well, so, of course we know the Earth better than all the other planets in some ways, right? But you might want to ask yourself why it is that plate tectonics is a relatively new theory. And one of the reasons for that is that we actually only see 40% of the Earth clearly, because the rest is covered by oceans. And when we when we try to understand the Earth as a whole, actually a huge part of that story is missing if you don't know what's beneath the oceans. So a lot of what we don't know is because we didn't have good ways to look at things. And so actually sometimes you go to other planets, and we've sent probes to other planets. You go to other planets and you find that we see more of the surface, and we can see in great detail because they don't necessarily have the same atmospheric weather that we do. So other planets and other parts of the solar system, moons of the giant planets, we can look at those and try to understand them with the same eyes that we use to look at the Earth. To tell the story of how they're different, you can look at something like Venus and Earth, and they should be really, if you look at the ingredients for that recipe of how you make one of those planets, both are sort of made to the same recipe.
Right.
They're sort of big rocky planets. They have similar in size. All kinds of things appear to be the same. But when you actually look, when you observe through the atmosphere of Venus, which we can do with radar, you see a world that's very, very different from the Earth. So there's no oceans, but also there's not really mountains in the same way. It's mostly volcanic. You see massive amounts of volcanoes, lava flows, all the things we associate with volcanic eruptions, just planet-wide.
Wow.
It's a really amazing place. But it's very different from the Earth. It's horribly inhospitable, but that's only part of the story. It really doesn't seem to have plate tectonics at all.
Right.
And it's a puzzle why that should be. Because normally you look at two things that are the most similar in size, probably very similar in the way that they were put together, and you'd have to ask yourself why they come out so differently. Yeah. There's no family resemblance, if you like. So that's kind of an interesting place to start, that sort of understanding why they should be different.
Right.
But if we look all around the solar system, it's the Earth that's the one that's most different. In the sense, it's the black sheep, right? It has this very different sort of behavior. It's got its surface dominated by plate tectonics, and almost everywhere else is not like that.
Right. So that makes Earth unique.
It makes Earth unique.
Right.
So, I mean, it's worth sort of explaining what that is, right? So the plate tectonics is something that came out of the fact that we suddenly were able to observe beneath the oceans after the Second World War, right? So there's a lot more imaging of the subsurface associated with the fact that there were fleets of submarines and people wanted to know where they were, and all kinds of other things. We had a flowering of seismology because of the need to understand what was an earthquake and what was something more sinister, like a test of an explosion, right? So there's sort of that observational aspect of geophysics really took off, and people realized very quickly that it was very different under the oceans to what we saw elsewhere. So if you strip off the oceans, you see something quite different. You see these sort of systematic mid-ocean ridges, which are mountain belts right in the middle of the oceans, great trenches. You see all this structure, but in terms of geology, it's kind of like one thing. You just see the bare plates. And the plates are these big blocks of the Earth's crust that move around, sort of grinding on each other, but they're almost rigid by themselves. So we see them moving, and they really do move. They move at a few centimeters per year. So you see these things moving, and really what it means is that, well, they move 10 centimeters a year, but they do that over hundreds of millions of years. So that's tens of thousands of kilometers. Really, it adds up, right? So what it means is that the Earth's actually turning itself inside out. It just continually recycles its surface into the interior.
Oh, interesting.
And forms new parts of the plate. So the theory of plate tectonics is sort of about that, and just describing how that works and thinking about the mechanics of how it works. So it was the big discovery in the geosciences, in the earth sciences, in the last century, and it's still the sort of big discovery. It's the way that everything works, right? It ties everything together. But it's an extremely interesting puzzle that we don't see it anywhere else. So we don't see the movement of the plates. We don't see anything as sort of driven by tectonics as we see on the Earth.
Oh, so there are plates anywhere else. We just don't see them moving.
We don't see it. What we would be able to see. We would be able to see the effects of the plate movements. We know what to look for.
Yeah,
and we don't see it. So all the other planets have one big plate. So it's got no boundaries and joins, and probably means that they don't have. Well, I'll say earthquakes. Obviously, they're not the Earth, but they don't have the same thing as earthquakes. They might have volcanoes, but they don't have volcanoes in the way that we do, in quite the same way. So it's quite interesting. It's very different.
Yeah. And how do they move? And I think so. Over the years of Earth's evolution, it would have the plates would have evolved and moved as well. Right?
Yes.
So how do they move, and what's their role in evolution over time?
Okay, so the way to think about that is that there are these two different parts of the Earth. There's the part that we stand on, the continents, and then there's the oceans. And of course, we think of the oceans as being the hydrosphere, the water, and everything else. But underneath the seabed is the plates, and the plates really are they're formed at the mid-ocean ridges. They're at these mountain belts that are in the center of the oceans, and then they sort of fall away, and they go across. Like the whole of the Pacific Ocean is almost one big plate, and it's formed at the various places that are the mid-ocean ridges where the new crust is being generated, and it all goes along, and over thousands of kilometers, it floats along on top of the Earth's mantle, and then it reaches the Great Trenches, which we call subduction zones. Yeah, which is where where the plates turn around and dive back into the interior. Okay. So then, after 100 million years or something, you form the plates very young, transfers itself across, and creates a big circulation, a three-dimensional circulation in the interior. Which we can think of in the same way as something like a lava lamp, that you've got heat generation in the deep earth. It creates this circulation, and what you see is movement. And you see this movement of the plates, but it's really a reflection of a big three-dimensional circulation underneath.
Right. That is happening over thousands of years.
It's happening over millions of years. Millions of years, yeah. Wow. You wouldn't see much. Even 1,000 years, you don't see a great deal.
Right.
And actually, we don't see a lot because it happens. The process by which these movements happen is, at great depth, is sort of smooth lava lamp-like motion. But what we see close to the surface is earthquakes. So the motion is sort of jerky and sudden. It adds up. It adds up to a few centimeters per year. But you don't see something happening every year. You see a great big earthquake every 50 or 100 years. Yeah. And you see lots of little earthquakes in the meantime.
Yeah.
And that, as that happens, so we're not sort of aware of this gentle creeping. We're aware of the sudden snaps as things jerk from one time to the next.
Yeah. So how do we measure these tiny changes over thousands of years? How do we know it's 10 centimeters a year, you said?
Yeah, roughly, yeah. That's the speed limit, it's around about 10 centimeters a year. Some go slower, and some are speeding, but mostly it's about 10 centimeters a year. Not very much, right? But it adds up. A decade, it's
tiny.
a meter, right?
Yeah. And
so we know it's moving because we've long been able to measure it because centimeters per year do add up, and you have to be able to measure something accurately over long distances for that amount of time.
Yeah.
So people were able to do that. In the 1960s, people could do that by looking at things like satellite laser ranging, where you bounce lasers off satellites and back again, and you can measure very accurately what the distances are. You could also measure, you do sort of interferometry with telescopes, and you can look at quasars, and you can say, well, these two telescopes are actually moving apart very slightly over a course of a decade, and you can plot a line. Right? So that tells us that, we can directly measure some of these things. But we can also measure it the other way, which is to say, well, if something is moving over tens of thousands, millions of years, then those motions accumulate. And one of the really big observations that was sort of one of the proofs, if you like, of plate tectonics was the connection between the formation of the plates and reversals in the Earth's magnetic field.
Oh, okay.
So what happens is that the Earth's magnetic field periodically reverses.
Yeah.
But not like a metronome. The period it's sort of quasi-periodic. It flips back and forth, but there's irregularities to that. So what that means is that the analog that people used to use, which is not so common these days, is that it was rather like a tape recording the magnetic field into the molten rocks as they formed at the mid-ocean ridge. And then as the sign flipped, you would get these sign flips that just would propagate off down, and you could measure them. And you would see the effect of that is the sort of just a pattern of stripes all across the seafloor. And they're really everywhere. And so you can just go anywhere and you can see this little barcode of these reversals, and you take a ship and you go and you measure it, or you take a satellite and you measure something. So you can do all those observations, and you see the pattern of the aging, right? So the young to the old. Magnetic field's global, so you have the same patterns appearing in different places, but if they're of the same age, then you'll see the same little patch of barcode from one place to another. And people have used that observation, and many others, of course, to be able to create these relative dates of the ocean floor. And actually you can go and dredge bits up, and you can measure the radioactive decay ages. You can measure this melted and it trapped these isotopes, and they evolved. So you can connect all these dots. Right, I told you it was going to all connect dots everywhere in the story. You don't really realize what's coming, right? Oh, we have to pull in this thing from over here to understand how that worked. But so then you've got like measurements that we make over the space of a decade that say, okay, there's a few millimeters, and we've got this velocity, and you've got measurements you make of movements that occurred over 100 million years, for example, and you can measure an average velocity. And it's quite striking that they almost come out to be the same.
Interesting.
So on average, you can sort of plot a line, and they come out very close to being the same.
Yeah.
So we can measure it right now, and we can measure in the geological history that plate tectonic, the sort of the influence of plate tectonics.
Right.
All right. So that works for the oceans, but the continents.
Oh yeah.
The continents are the other bit. And if you look, so it is almost like two different worlds kind of smashed into one, because the continents are not part of this big overturning inside-out circulation in quite the same way. They just sit there and get pushed around. They're pushed around. They act to help direct and orchestrate some of the motions, but they're still there. And especially here, sitting in Australia, we've got can go and date rocks that are 4 billion years old. So they haven't been down in this big circulation. They've just been part of
billions of years.
Australia or Gondwana or whatever for all this long period of time. So those rocks are really very much older. So we know that that part of the story is not systematic in the way that plate tectonics is systematic, like I just described.
Yeah.
So it's a different story, and it explains, for me anyway, it explains why we didn't discover plate tectonics straight away, because we were only looking at the half of the Earth, and it's a very different story for that half.
Yeah. So with this unique feature of plate tectonics on Earth, is that, and I'm sure it is that life being on a planet is in a way related to having tectonic plates?
Maybe.
Are there studies or evidences that has correlated that?
Well, we can't correlate it because we only have one example.
Yeah.
But we can look at some of the one of the reasons people think it might be very helpful to have something like plate tectonics to create life or to sort of support life is that because the Earth is, because in a plate tectonic type world, the Earth is turning itself inside out, as I mentioned. That's bringing up all this new material, all the interesting outgassing from volcanoes, lots of new resources. The chemistry is very different. It maintains a slightly different atmosphere as a result of that. So worlds where the surface is sort of stagnant, it's actually, stagnant's a technical term for that sort of thing, where, like the moon or something, where what you see all over the whole moon is basically been like that for a very, very long time. Those kinds of worlds have no communication really between the interior and the surface, and so the amount of resources you have is limited. So it's not the only requirement, but it's one of the requirements probably, is to have these sorts of tectonically active worlds.
That's interesting. But so this movement itself, this fresh stuff coming out on the surface, that's not anywhere else, or it's less prevalent anywhere else. Why is that happening in the first place?
So we don't know, because we've got this problem, which is so it's not quite true that it doesn't happen anywhere else, in the sense that we think of, so there are sort of different categories of this sort of this communication between the interior and the exterior, and one is that there isn't any real communication. You form a stagnant ball and that's rock, that's it, right?
Stays like
and
that.
Whatever's happening underneath happens. You may get heat coming through, but you don't necessarily get a lot of material coming through. You'll probably still get volcanoes, you get all sorts of other things, but it's not quite the same set of processes. There is another sort of category of this, which is sort of an episodic catastrophe, where which we've never observed, but it's sort of there in the theory, which is where the planet turns itself inside out, but instead of nice regular kind of even 10 centimeters per year, it'll be nothing for 500 million years, and then the whole thing will just overturn like a chaotic foundering of the whole surface and disappearing into the interior, and you start afresh.
Oh wait!
So that's wiping it all clean.
No,
but
that's not happening over a long period of time. You said it happens instantly, or
instantly is relative, right?
I see.
Yeah, I mean quickly compared to the kind of timescales we're worrying about for the formation and evolution of life.
Oh, and
so we thought Venus might be like that. I don't really know if that's still the case, but Venus has a sort of certain surface age, and it's neither very young nor very old. So one possibility was that it just suddenly kind of
flip and
had some sort of fit and just turned itself inside out, and then went back to being volcanic again. So that's one possibility. and then there are sort of very volcanic worlds. Some moons have this very different sort of, really, really intense volcanism all the time, which is communication. It's also it's also unclear if that's conducive to life. But I think the issue we have in trying to understand if this happens anywhere else is that the Earth is sort of it's the biggest of the Earth-like terrestrial worlds in our solar system. So we don't really know whether that makes it a little bit exceptional because it's slightly bigger than everything else, or if it's some contingency, something happened along the way that made the Earth different. So it's really hard to predict from that, and we would like then to understand things like there's tens of thousands of exoplanets that we've observed, and many of them are gas giants, but many of them are not, and they come in all sorts of different sizes. So we're starting to discover many sort of super Earths, and we don't really know whether the super Earths would be great places for life or not.
Yeah.
And to detect that, we wouldn't probably try to find out about plate tectonics. We would look at the atmosphere and see what we could see in terms of disequilibrium and other things, right? But people would like to know, well, what's the typical percentage of these great big exoplanets that might have plate tectonics or might be catastrophically volcanic or whatever?
Yeah.
And unfortunately, we don't really know because it's really a hard problem to fully get to grips with, trying to understand what is it that makes Earth, what is exceptional about Earth versus what is not, when we don't have the ability to go and see we can't put Earth in the middle and look at either end of a spectrum,
right?
To say, plate tectonics, then more plate tectonics over here.
Yeah. How well can we study Earth itself? So we can't so readily access interiors of the Earth as much as we'd like. How do we study, apart from modeling? Are there any physical experiments or?
Yes. There's lots of ways to try to figure out what's going on inside the Earth. So many of my colleagues are seismologists, and seismologists use essentially sound waves, very slow sound waves that are bouncing around inside the Earth to do imaging. Okay, so that's kind of like doing an ultrasound, but instead of using high frequency sound to make an image, use very low frequency sound, which is naturally present in the Earth anyway, from things like earthquakes and volcanic activity, but also from just the ocean waves beating down, and all these other things create all this spectrum of noise that's going on in the interior of the Earth. And if so the first sort of seismic experiment, so you have a big earthquake, sends all these signals out, and you measure them across the Earth with seismometers of one kind or another. So if you do that, you can essentially go, well, if the Earth was just a big ball, like a billiard ball or something that's completely homogeneous, then it would take this long for the waves to get across. They would just go from there to there, and that'd be it. And you might get some waves that travel along the surface like this, and then they would take so long, and some would go around the other way and they would take longer. So in fact, it turns out that's not what we see at all. We see these very different behaviors, and part of it is because, well, the Earth is very, very large, and it has a hot interior, and it also has a very, by the time you get to the center, it's very high pressure. So there's lots of changes on the way down. So we're familiar with the Earth's crust. That's where we live. Spend
most of our time.
So the crust is very different between the continents and the oceans. The continental crust is generally a little bit thicker. It's a little bit lighter, not by a lot, but the rocks are a little bit lighter, and they have a tendency to sort of float and not participate in this overall circulation. The oceanic crust is a little bit different to that. It does get recirculated, but below the crust we have the mantle. So the crust is depends where you are, but it's 10, 20, 30 kilometers thick.
Okay,
that sort of amount. That's on a ball that's 6,700 kilometers in radius. So it's really just a little thin veneer
layer,
on the top. And underneath the crust, you have the mantle, slightly denser rock, and then there's 3,000 plus kilometers of that. So it goes about halfway down. Mantle's solid. We can estimate that it's silicate minerals of some kind. You get down to the bottom of the mantle. You get to the core, which is mostly iron. It's mostly molten too. So the mantle's solid. The crust is mostly solid, right? And then you get down to the core. The core is molten, and it has a little dense ball on the inside of the inner core, which is solid again.
Okay.
So there's quite big density variations as we go down, and those allow that we can image that, right? We can see those density variations because it means that a wave starts from an earthquake. A sound wave coming out tends to curve down and then come back up again.
Ah, I see. Yeah.
By a process of refraction. But if it goes deep enough, it might bounce off the core
because it's solid.
And so you go, oh, that was unexpected. What was that?
Okay.
What was that? Some things might go through the core, but not everything, because it's a liquid. It can't transmit shear waves. So there's all kinds of interesting things that seismologists discovered, and they did that painstakingly, earthquake to seismometer for many, many years. And then over time, that's become much more of a sort of, a sort of big data imaging problem, where you sort of throw everything in, and you start to understand all this cacophony of the seismic noise, and then you just start to use these algorithms which can sort of tell you, given all of these paths through the earth, all of these different sources of noise, all these different receivers, what's down there, and create some very beautiful images as a result.
Yeah.
So that's what we call tomography, and it's something that comes out of medical imaging, of course, right? You have a CAT scan, that's tomography. So those things become somewhat automated almost, right? That you just wait and you see more and more beautiful images. So seismology is one of the ways we look inside the Earth. It's not the only way, and we can see variations in the Earth's gravity. We can see variations in the Earth's magnetic field. We can see we can sample things that came out through volcanoes. There's all kinds of things. Some pieces of evidence are, real, what we might call ground truth, right? They're really bits of information that have come from somewhere, and we can observe them. Some of them are what you'd think of as remote sensing, where you look at you can't actually go there, but you can send a sound wave, or you can send a signal, a radar reflection or something like that. So we actually have a reasonable understanding of what's inside the Earth. Can't really do seismology from space, so we don't have all that much information about what's inside the other planets. There's been seismometers on the Moon, there's seismometers on Mars, but not many, and we haven't had 50 years of planetary seismology to say, well, this is what that is and this is what this other thing is. So we're still a little bit in the dark there. And that's where modelling and things that I do sort of bridge some of the gaps between observations we can make in some places, the laws of physics, if you like, and things that we can't really observe. We can't observe them happening, but we see them indirectly.
You mentioned that the core of the Earth is iron, solid, and so there are two pieces of the core. There's a center and the outer layer of the core, right? The outer layer is
that's the liquid one.
That's the liquid one.
Yep.
But it must be really high temperatures.
Yep.
And inside of that is a solid iron core.
Yes. Probably mostly iron.
Mostly iron. Okay. And then the mantle itself. Talk a bit about mantle convection and how sort of the overall. Why is it important for understanding Earth's behavior over geological time?
Yeah. So mantle convection is this lava lamp-like process, and one of the things that's important about it is so if you look at your high school physics textbook, it will tell you how heat gets around. It can be, radiation, radiation conduction, and convection, right?
Yeah.
And that's very familiar. So of those, conduction, you can't see when heat is conducted from place to place, then you don't see it. It's just something that happens within the material. Some processes are happening. Electrons move, or sound waves move. These sorts of things, and transfers heat energy from place to place. Radiation, you hold your hand up and you can feel it. There's no movement involved in either of those. There's movement of photons, but there's not really material movement. But the lava lamp is all about movement, and convection is all about movement. And it's a heat transfer process which is dominated by advection, which is like I take my hot cup of tea and I move it from one side of the table to the other. Now, on average, this side of the table is now colder and that side's a bit hotter. But all I did was to move something. And so I move the hot stuff from place to place, the average temperature changes. So convection's kind of like that. And the movement occurs because of buoyancy, because the hot air rises, that's convection. So the thermal buoyancy creates these buoyancy forces, and they in turn create movement. So if you've got heat energy sitting inside the deep earth and it tries to get out, if it moves out by conduction, there's no motion. If it moves out by radiation, there's no motion. But if it moves out by a convective process, it has to create some sort of movement. So it's the heat engine, right? If you get movement out of dissipating heat, you've got a heat engine. So convection is important because it is actually the energy source for all the geology that we see, all the plate tectonics. They have to have some sort of energy source, and that energy source is heat loss, and it must be by convection to create the movement. So little tiny planets or moons, asteroids, they just cool off probably by conduction, and they never get to a sort of convective state.
Process, yeah.
There are reasons for that, but one of the things is it's losing heat by conduction so fast that things don't get a chance to move. They just become cool, so it doesn't matter. But the bigger planets, as the heat tries to get out, it builds up and creates this convective overturn, the same sort of thing we would see in the weather, the clouds forming and all this sort of thing. The energy is supplied at depth and it tries to escape to the surface, and in doing so creates movement. So it's the energy source. It's also important to think about where that energy comes from. It's not just the cooling of the Earth. It's radioactive elements decaying in the deep interior. So most of that is probably in the mantle.
In the mantle itself.
Yeah, and so those, there's a lot of uranium, thorium.
That's where it all is.
Are there, and as they decay, they create they create heat, and the heat has to get out. So it's more of a puzzle for some of the bigger planets as why they don't show this at the surface, why we don't see plate tectonics. How does the heat get out?
Oh, yeah.
It's always the question. How does the heat get out then? Because they must be getting hotter if they've got radioactive material in them.
Yeah.
So mantle convection is sort of the reason it's important is that it is the driving force for these things, and if we understand it for the early Earth when things were probably hotter, and we understand what it was like then maybe we understand it better for other planets, which might be bigger, maybe have more energy sources, or maybe smaller, fewer energy sources. And so that's sort of the way I think of it as being sort of an important process to study.
When we look at the Earth from, let's say, 4.5 billion years ago and now, and thinking of the formation of the layers,
yeah,
right? Are there timestamps in a way that we've measured during the formation? In the sense, if you look at Earth forming over millions of years,
yeah,
what's the story like? What happened over millions of years?
Okay. So once upon a time.
Once upon a time.
Kind of thing. Yeah. So, I mean, one of the things is that, we don't know exactly when to start the clock.
Right.
And one of the reasons for that is that the Earth would have formed, the solar system forms, everything's in some sort of, very chaotic state of forming the sun. You form all of this material around the sun that's condensing out. And you would tend to create nuclei around which things accumulate. So maybe sort of balls of dust and rock. But after a while, they start to accumulate, and then when they get big enough, then they interact with each other gravitationally, and they start to try to coalesce. But now you've got these sort of mini planets, not just grains of dust, but little mini planets that are coming together.
Yeah.
And those collisions repeatedly reset the original planets. They're big planets coming together. So the Earth's a great case in point, because it was hit by something the size of Mars during its early formation, and that collision almost certainly created the Earth-Moon system. Right? So we hit it. We start out with something. So it was the Earth before, and then it was the Earth and the Moon after. Well, it was the Earth plus a big thing coming in. They spend some time colliding, and then over the next few days, you coalesce these two new planets in orbit around one another, and we go, oh, that's the Earth and that's the Moon.
Right.
So all the planets form in the same way, and it's not obvious that you would then sort of go, well, okay, that's finished now.
Right.
Because you still have a rain of material coming down.
Right.
It just doesn't get significant enough to break the planet up. I think that's probably how you'd think of it. So that's sort of the first period, if you want, the first act of the play that is sort of the Earth forming. And so, we don't have much evidence from that time. It's continually being reset. And the kind of evidence we have is sort of, circumstantial, that we know we can see how the Moon is different from the Earth, and they may have come from the same, the same collision. Stuff. So we've got sort of, this ended up here, that ended up there. Why would that be? But if you look at the Moon, actually, you can sort of see its history, right? There it is. There's a lot of craters on it. It was initially hit by an enormous amount of material. We can see the flooded basalts that are the lunar maria, right? You look at that, and that's 4+ billion-year-old surface, and nothing much else happens, right? But for the Earth, it's a very active world, so we would have had this sort of Hadean Earth, where we have, it's just really it's still melting everywhere, lots of volcanism, all kinds of things happening. And then we move into sort of what we call the Archean, which is everything between that sort of formation period when we started to get an actual surface that it persists, right up to a couple of billion years ago.
Okay.
So that's that's half the Earth's history, right? But the thing about that is that we still have Archean rocks, and not just like fragments. We actually have Archean terrains, if you like. We have whole portions, which we tend to call cratons, which are these sort of almost undisturbed blocks of the Earth that have come through. And Australia's chock full of them. You go out west, that's mostly what it is. So we can find bits of that surface, and we can say, okay, well, this is something from the Archean. And of course, there's sort of evidence of life at that point as well. But really, you get this sort of transition to, you then get a transition to a sort of a different style of deformation and other things that we see in the Proterozoic. And then we start to, and then you start to say, well, okay, well, we probably established, it's not completely, people will argue, but we probably established plate tectonics and similar cycles in the sort of rock record to the ones we have today. So, the sort of overturning and everything else. And you would instead sort of go, well, so when we're trying to understand what's happening, maybe what we're much more interested in is the near-surface record of how the individual places kind of formed. And we're talking about bits of the crust. But almost all of our story there is related to the evolution of life over that period. And I'm not an expert in that part, right? So I'm not going to try to go too deep into that. Yeah. But, all of our sort of individual geological timescale, if you like, when you look through it, it's all really predicated on the types of animals and types of plants that are around at any given time. And that have left their sort of imprint on the rock record.
Right.
The rock record is sort of interesting as well because, it's not accidental. We've got gravity pointing downwards, and so things settle into big flat layers, and they gradually sort of get buried by one upon the other in this sort of in this cycle. So we are creating this sort of when we lift something up, we immediately expose it to erosion, and it settles down and it runs down back into the oceans or back onto the plains, and becomes part of our sedimentary record. And we see this endless sequence of cycles running through as we do that. And we used to date them all by the fossils. We still name them all through the fossils. But, that sort of tells you something about what we're interested in as much as anything else, right? This is the bit of the crust.
Yeah.
But incidentally, I suppose it's interesting if you think about the age. So we've got rocks that go back to that 4 billion year history, right? That tell us some of that story, and we can look at the minerals and we can understand what those rocks are. If you go into the oceans, though, they're almost all gone because of this sort of convective process. Almost all the oceanic crust is gone after 200 million years. It's sucked back down again. So that's sort of 5% of the age of the Earth. And the rock record that we're interested in is on the continental rocks, goes back for that full, 90%. So they're very different. There's a very different recording there, right? And the primary process is, for the Earth anyway, the primary process is all the overturning. Right? So the heat engine is churning the oceans over and churning the seafloor over. But what we record is everything else. So the primary process is not what we record. We record the secondary process of the continents being shifted around and having volcanoes erupt on them and all these other things. That is not the first order driving force for this problem.
Yeah.
So it's an interesting observation, that one, that we sort of are looking at always at the sort of indirect recording of what was really going on.
There isn't much of a choice, is there?
There's no choice.
No choice.
Yeah.
But the computational models are a good alternate, aren't they? So when are there models which, so the 4 billion years that you just described, are there models where, for instance, you took ball of gas coming together, and then what you find at the end is similar to what Earth is like now?
I wouldn't necessarily believe them if they do that.
Yeah.
And the reason for that is so much of that history is, you could call it stochastic, or maybe we just call it circumstance.
Random,
yeah. So we don't know which little things collide and what they were made of. And we sort of have this assumption in a way that the process of all these collisions homogenizes everything. So one planet and the other planet might look the same. Broadly speaking, we threw the same things in. But it'd be very surprising, given how different the planets seem to turn out, and how it'd be very surprising to come up with a random, roll the dice a few times and come out with something that was Earth-like in sort of a meaningful and interesting way. So I think from that, people do models of trying to understand how the solar system condensed and how the planets formed. And the questions they would probably ask would be much more around how many planets, and how do they, what do we know about the planets that are formed from things like how they spin, how many moons they have, are there distributions in the solar system that are important indicators of history, the history of that formation. Did presence of Jupiter mean these planets, no planets can form here, they all form there. These ones have moons, those ones don't, these ones have collided. So we would learn those kinds of things, and we would sort of say, okay, that's what we learn from that process, but we get sort of an Earth of some kind. So let's start again. Let's try to understand, if we did get the Earth, how would it evolve through time?
How would it get the plates?
Yeah. And so the process of computational modeling really is to say, well, we have all this, we have information about how the Earth formed, but it's very limited information sometimes. So rather than trying to, it's almost impossible for us to go back and fill those gaps, because it is forensic, right? We've got stuff's missing from that record. We just can't figure out what that is. But we're not completely in the dark in that regard, because we do know that physics and chemistry and biology have been working on this problem. That's how it got there, right? We have this knowledge as things move along. We know something about the fundamental processes that produced it. So where we have some information, we can say, okay, from that information, we can work forwards and say, okay, well, it followed the laws of physics. We understand the chemistry. It must have done these things. And we can start to estimate how those processes interact and play out, and understand something about how we got to where we are today. If we know what we've got today well enough, and we know the physical processes, we might even be able to work backwards and say, okay, well, what is it that what did it look like before, and how did that evolve towards now?
Yeah, but it's such a long way back.
Yeah, and so many of those, there are these sort of points where everything is really, in a real formal sense, it's sort of erased all the information. You can't go back through some things, because they've just taken there is no way to see. If you really stir something and completely stir it up, then that information really does get lost, and you can't tell what was there before. So you just have to, there are places you get stuck, or there are places where it's absolutely not unique. Many things could have happened and they will all end up at the same place, and so you sort of can trace something back and then go, well, that's something, but I can't necessarily tell you with precision.
So there's no case where a model can get up to tectonic plates being built?
We're close. We're close on that, because I think we do understand the ingredients. One of the reasons it might be difficult is that it is sort of dependent on sort of the history. So what you see is what you had before. Things get stuck in things that sort of get into a rut and stay a certain way for a long period of time. And there may have been some small accident of fate that a fault forms, like the San Andreas fault forms, and once it's formed, it's the dominant feature, right? It controls everything. But why that one and not the next one over, and various other things, right? So you will be able to answer some sort of general questions and say, we can make a world with some plates. What are the questions we're interested about? What are the questions we're interested in answering about our world?
Yeah.
So I think there are two directions you can go with those kinds of questions. You can ask the real basic science questions, and then you can the other way you can go with that is to say, is there something about knowing how the Earth works today, and knowing something about the physical processes how it got there, that you can that we can use that information to make predictions on a useful scale, a useful time scale. I mean, I can predict, I can make a prediction about plate tectonics stopping in 4 billion years' time, and I don't suppose people will be all that interested.
Right.
But what we might be able to do is say, okay, well, there's all these faults. We know how they work, and we can image the interior of the Earth, and we know sort of what's there. So at some point, we're going to be quite good at saying, okay, let's see how they move. What's going to happen over the next 10 to 100 years. Maybe not for things, maybe to try to understand which parts of the Earth are more susceptible to sea level change, for example, because it's moving up and down. We need to create some measurements. We need to understand how the Earth's dynamic state feeds into these kinds of things we're trying to understand.
Yeah, I'm thinking of something more sinister, like let's say if Earth is the only place which has life and tectonic activity, and we want to settle on Mars,
Yes.
is there can these models, or can we understand tectonic plates formation well enough that we can induce that on Mars or somewhere else, right?
I doubt it. I doubt you can induce it. Yeah, I don't think you can. Yeah, okay. So I don't think you can do those things without. You can imagine it's sort of like a terraforming of
planet,
Mars, right?
Yeah.
You'd have to be very patient, because I suspect you'd probably find that what you needed to do was what we talked about before: smash some other planets together, mash them all up, and then wait 100 million years or something. I imagine that that's not probably what you would do.
Is that part of life cycle of a planet? So all of these planets would be, probably my wild guess, is at a different time of their life compared to each other as well. Is that right? And then I don't know. Do we understand that for example, Venus is, I don't know, certain years younger than Earth versus the other planets, and then they're at a different on a path to maybe become like Earth, or were like Earth.
Yep. So we, so they all formed around the same time. So now we're talking about sort of the equivalent of cat years and dog years and human years and that kind of thing. So we think smaller planets are more able to lose their heat more quickly. Okay. So this is sort of this is familiar, right? So you have a relatively large surface area to volume. So we would expect smaller planets to kind of live shorter lives, probably. But we can always be surprised by that, because we don't know that a big planet that suddenly starts plate tectonics and turning itself inside out might actually get all of its heat out suddenly, and then run out early. So it's all very unclear. What we know the end state. Eventually it runs out of heat and everything must stop. So it's true for the Earth, and it's true for Mars, it's true for Venus. So eventually they'll run out of radioactivity to generate any more heat, and they will eventually run down to nothing.
Right.
But we really don't know. There could be some surprises along the way. We really don't know what the sort of whether any of these sudden episodes of overturning might occur, because as they're cooling, their sort of outermost plate, their single plate gets thicker and thicker. Maybe it does get dense and overturn. We don't really know that, right? We don't know. But we tend to take a sort of conservative view and say, well, they're probably winding down. They haven't shown much activity over 3 or 4 billion years. So, we look at Mars, and it seems to have been sort of briefly habitable with the atmosphere and various other things. Surface water. But that's not a very long-lived period of its history, and it's dry and desiccated, and there's not much going on there now. Venus is kind of an really interesting example, because currently it's the sort of it's dominated by runaway greenhouse atmosphere, very, very hot surface. And it is very volcanic, right? But at some point, the sun wasn't always quite as strong. So at some point, Venus probably was a little bit more kind of cooler, and maybe you can ask the questions: was it actually the sweet spot earlier on in the solar system's existence? Was it more of an interesting place to go and live? I don't know the answers to those questions, and people will debate that sort of thing. But you can try, there's little fossils in the atmosphere of whether or not you lost a lot of water, for example, would leave behind an interesting signature of the ratio of deuterium to hydrogen or stuff like that. It will tell you how much water you had, how much you lost, how much was stripped away. So a lot of those things we don't. I mean, I can't give you any kind of interesting answer, but there's some interesting speculation about what the planets might have been like in their past. Yeah, I mean, there's a whole universe out there probably full of planets, and it's just as interesting to imagine how many of those might be habitable, and what that ratio of habitability to uninhabitability might really look like,
right?
For other solar systems.
But the tectonic plate seems to be the key. So the plates and earthquakes, right? They are they as random as they seem, or do we understand that how they're connected?
So to me, they don't seem entirely random, but some bits, we have the notion of plates, and plates are these sort of big, strong blocks of the oceanic. We call it the lithosphere, the plate itself, right? And those are, relatively speaking, inactive from the point of view of earthquakes, right? But the boundaries between the plates are where all the action takes place. So those are very narrow and well defined. They show up quite clearly if you were to plot a map of all the earthquakes, and these days it's quite easy to do. You can just go to a website and ask for all the earthquakes over some period of time and between some range of magnitudes, and you'll very quickly see the plates appear. And all the plate boundaries will appear, and everything in between them is the plates themselves. So you'd see that quite quickly, and it's again, it's quite a surprise that people didn't spot this before, but it's only with hindsight that we can say that.
Now you can,
right? And it's so easy now to do it. It's really hard to remember that these things were very, very difficult. Every point was hard won. So they're not random in the sense of, we know places that are likely to have earthquakes, and we know the kinds of earthquakes they're likely to have. Shallow earthquakes, deep earthquakes, because we understand the physical processes that are behind behind those earthquakes happening. We know why they happen. But what we don't know is when the next one's going to happen, right? Which is where the real questions sort of leading.
Yeah.
That we don't know. We know a little bit, right? Because we can say, all right, what is it that's behind an earthquake happening? And it's very simple principle. So you have two blocks of rock sitting together next to one another. In between them is something that we would call a fault, a sort of a separation between the two blocks. And there's some forces on it, right? The tectonic forces are acting, and they might push the rocks to slip, right? They tend to slide past one another. They don't, they're sort of a bit like cracks, but they're not opening up. They're sliding. And that's just because they're usually under a lot of pressure. So they're locked, they're ready to slide, they reach a critical point, and then they suddenly slip. So we can tell that there are places where there is a lot of tectonic stress building up. But it's a little like, there's lots of kids' games that are based on this idea of, you get something that's about to happen, and you know it's going to happen, but it never seems to happen.
Right.
You balance sticks, right? There's all these games that you would play. Jenga's another one. You something's going to fall down if I pull this piece out from underneath. But you can do that for a surprisingly long time before anything actually happens. So when we look at a part of the Earth's crust with a big fault in it, and there's lots of stress, and there have been big earthquakes in the past, we know something will happen. Tectonics doesn't just stop. So we know something will happen, but we can't tell if it's going to be
when.
Yeah. When's the next big earthquake going to happen? Lots of little earthquakes are always happening, but when's one going to turn from a little earthquake into a great big earthquake and cause all kinds of trouble for the people who live nearby? So we can't really tell that, and one of the reasons it's so hard is that it's very hard to predict these things which start out small and then just catastrophically cascade into something that's very big. Earthquakes have those sort of properties. We always get lots of little earthquakes. People are not usually very scared of them. But occasionally they'll be a bit bigger, and we all get very nervous. Is that the sign of something big coming? Or was that just the biggest one for a while, and it's actually the sign that there isn't anything coming? We don't know the answer to those questions for the most part.
And that's because there are lots of pieces that result into the earthquake, or to what level the stresses should build for it to occur. We don't understand it well enough.
It's not just a measurement problem.
Okay.
I think that's the point, right?
Yeah.
You know, we it's not just that we don't know the stresses well enough. What we don't really know is the internal structure of the faults themselves well enough.
How deep are they? We're talking.
Oh, well, you're talking a few kilometers usually.
Okay.
Some of the faults can be some of the. I mean, earthquakes will happen quite deep in the subduction zones, right, where cold material is going down into the interior. The cold plates are being recycled, right? As they're being recycled, they stay cold, and it's the cold parts of the earth that are more likely to have earthquakes, relatively cold, right? But we often worry about the faults that are right where people are living. You know, so I mean,
That's what
worried about it in
matters.
Japan, right? We're worried about the faults we're often worried about are the ones that are quite near the surface and will create a lot of shaking near the surface. And the thing is that they're always active. They're like sort of, you know, shifting sands, right? They shift, and every once in a while you have a big landslide. Every once in a while you'll have a little, or quite frequently you'll have a little landslide. And these things tend to be, they self-organize. They become a system that is quite likely to fail, but we can never quite tell if it's going to be a big failure or a small failure. And it's sort of, when systems have that property, your ability to predict is really a very difficult to be useful. It's like we can predict something, but it's not very obvious how you turn that into a day-to-day decision-making tool, right? Yeah. Okay, so there's I can tell you if you live in a place that's earthquake-prone, well, there's going to be this many small earthquakes today.
Yeah.
You know, if you go small enough, there'll be one a minute, right?
Yeah.
No one really worries about it. What they really want to know is,
The one that
should
matters.
I stay home? Should I go outside? Should I send the kids to school? All that kind of stuff. And we have no idea how to predict those things with any useful level of accuracy.
Right.
So we can tell that something's likely to happen, but we also know there's plenty of places where these big earthquakes are sort of, quote, overdue, right? We know something's going to happen tomorrow, 10 years.
10 years.
How useful is that, right? So that's not what people focus on, not what seismologists and earthquake engineering specialists and so on really worry about.
Yeah.
They worry about making predictions like, okay, if there is an earthquake, how do we make the buildings survive it? What's the biggest earthquake likely to happen? What can we do if an earthquake starts to warn people to do something
Early enough.
You know, I think it's also a matter of education. What should we do? What should we tell people? What should they do if they feel shaking? Where should you go?
Yeah.
Should you stay put? Should you run to the hills? Right?
Yeah. It's also about how long that movement is, isn't it?
Yes. Yes. But that's sort of the size of an earthquake and the length of time are actually sort of related to one another. So the more of the fault fails, the more
the longer
the more time it's going to take. The failure starts and the fault sort of unzips in some direction. The failure propagates along, and it may stop. Sometimes it restarts and it gets going again, and you have these little sub processes that happen. So you've got to, you know, that's what people worry about. How do you give people useful information that an earthquake is coming in a way they can do something about it in their real life, right?
Yeah. What I'm thinking is that with all this new computational tools, AI coming in, would it be helpful? Or helpful enough? Of course, it'll be helpful at some level, but do we have enough information for these tools to be, get us applicable solutions?
One of the things that AI is really good at is getting some of that information. So finding the little earthquakes and stuff like that.
Right.
So determining, determining what's an earthquake and what's just sort of some random noise that's picked up somewhere else. Being able to sift through the signals and find true earthquakes.
Great.
And that gives us the possibility. So that's not my area, but it leads to something I am really interested in, which is really understanding some of the faults that we can't see.
So how's that happening? So we have sensors active all the time, or is it okay? Can you explain that a bit more?
So we have, let's think about the progression of seismology.
Yeah.
And I'll tell you this from a layman's perspective. I think is that we started out with a few expensive, fancy seismometers around the world, many of them, in research institutions, but some of them deliberately set up to try to monitor nuclear explosions, for example, test ban treaty kind of thing. So systematically looking for noise around the world, right?
Noise. Yeah.
And people sort of then gradually progress to these sort of, using seismometers, just putting more and more, deploying them to measure regions of interest. And that information doesn't go away, so we're sort of accumulating more and more knowledge in that regard. But over time, we've got much better at managing information, right? So now we tend to instrument everything, right? So we put seismometers in buildings because all they are is really measuring the shaking. So you might want to measure a building is shaking for all kinds of reasons. And then they are actually seismometers as well. They can detect something. And we all have phones that have mini seismometers in. They've got an accelerometer. They can tell if they're being shaken.
Right.
It's very kind of low quality information, but you can start to use. You can see how that information, even if it's only a little bit of extra information, can start to go in. If you've got enough computing power, you can start to use that to understand something about the overall picture, right? So the other thing that's sort of like an opportunistic seismometer is the fact that people are now using fiber optic cables that are laid in the ground anyway as seismometers by using them as sensors, using the as the cable shakes and moves. So it just changes its properties slightly, and if you send a laser beam down and back, reflected off the little imperfections that are in the fiber, you can use it for imaging.
I see.
That stuff is just in its infancy, but you can see immediately that you start doing this all the time everywhere, you suddenly get lots more information. So that means that we really are recording information all the time. Seismometers themselves are getting easier to use. It used to be actually that you'd have to bury a seismometer, leave it for a year, then come back and take the data out of it, right? Well, now you just put a mobile phone in and unless you can afford the SIM card, right? Or you put a satellite signal, you put satellites and you start doing these things in real time from satellites. And there are people doing that now, that they just deploy a whole load of seismometers, beam this information to a satellite, get it back down again. That changes everything, right? And so now you have this ability to collect lots and lots of information very quickly, and you can start to synthesize that information into understanding all these little tiny micro sort of crackles of the faults just moving very slightly.
Right.
And you use AI as sort of techniques to analyze the information. You start to be able to image a picture of what's in the ground, where the faults are that we didn't know about. So that's our big problem, right? We don't know where they are.
Yeah.
You can see them at the surface, and you can see the huge big ones, but often often earthquakes are triggered on faults we didn't really know was there, or we had some inkling, but we don't know exactly where. So once you have a picture where you know much more about where those faults are and what their activity is, we can start to actually, then we can put those into the modeling approach and start to understand better what we could do with them.
Yeah.
Right. So I think it really is sort of. I kind of came at your AI question indirectly there, but I think the AI is sort of helping us do the imaging and it's helping us process the data.
Mm-hmm.
So who knows? Maybe we will actually get better at sort of understanding some information, precursory information to earthquakes that we weren't expecting to ever be able to measure, right?
Right.
Because we know, there's a fault over here and this other thing. We may see some patterns that will cause us some concern.
Yeah. One of the things I've always, we know a bit about it, but it'll be great to hear how these mountains form. Mountains and, these unique features of Earth, in a way, if we can call them mountains and volcanic activity. Talk a bit about them.
Well, what's your favorite mountains?
My favorite mountains.
Let's talk about those, if I know anything about it.
Yeah. I mean, most popular is the Mount Everest, of course.
Yeah.
Right? And the ranges around that.
Yeah.
Would you like to talk about that?
Yeah, that's a good one, because I can.
Yeah.
So thank you. So not staged. So the thing about, Mount Everest is part of the whole Himalayan
ranges
system, if you like. And of course endlessly studied for being sort of the most spectacular mountain range that there is to think about, right?
Yeah.
At least on this planet. So, but we do know quite a bit about how it forms. There's a lot we don't know, but we do know kind of the broad picture, and it's kind of like reckless driving on the part of India, right? So the Indian subcontinent comes roaring up. It really is breaking the speed limit. It comes up much faster than the 10 centimeters per year, probably, and roaring up from somewhere well down south.
Also, that rate of movement is different in different parts of the Earth.
It is different in different parts of the Earth.
Yeah.
So it's not the speed. Yeah. So the Indian subcontinent moved pretty fast at some period, and there's some beautiful animations of that sort of thing, which I would advise everyone to go and have a look at, right, to really get a sense of how these things move over the 100 million year time scale. But the Indian continent was moving, and of course it's attached to a plate, right? It doesn't move by itself; it's attached to a plate, and the plate was going into a subduction zone somewhere on the edge of what is the rest of Asia, right? And at some point, they hit each other, right? And the reason I'm talking about reckless driving is actually quite similar. So when the Indian subcontinent hits the sort of Eurasian block, it smashes into it, and it causes, so it just makes this great big indentation, right? It's just you push the continents together, and the continental crust that's sitting there has to get out of the way, and it does it it goes in every direction. So quite a lot of it just goes upwards, quite a lot of it goes downwards, creates a big thick block which tends to float quite high, and that is the part that becomes the Himalayas and the Tibetan Plateau and all that sort of thing. But some of it also squeezes out sideways, and so if you look at a map of the Himalayas, it's almost like it's flowing out sideways.
Yeah.
Right, to the east. It's sort of, all the crust is sort of has moved in great big blocks, and there's a sort of a big sort of part of that has come around, and actually sort of comes all the way around through Southeast Asia. Really, all of that is deformed in the same part of the same story. And the sort of India is going forwards, and Indonesia sort of rolling back this way, and it creates this big circulation. But it's the immediate sort of impact of the collision. It's a slow motion collision, right? And it's still ongoing, of course, because we still are building those mountains higher. Excuse me. But it's that process. It thickens the continental crust is like 60 kilometers thick or something there, and it just floats a little bit higher, and that's why we have, 9-kilometer high mountains in places there.
Mm-hmm.
But it really is the most spectacular example. It thickens the crust, and the crust builds up, and then sort of gets to a maximum thickness. It's like, well, I could get thicker, but actually it's easier for it to just keep moving this way and thicken more of the crust. So all of the sort of interesting things that we're interested in these processes, which we call orogeny, but is really mountain building, all of those processes are sort of present in that particular example.
So the whole of the mountain is part of the crust only, or the other layers of the earth, is there any of it in the mountain or just the crust?
Well,
don't know.
Mostly it's the crust.
Yeah.
For the most part, you've thickened the crust and you've made some mountains. If you look in detail, right, you don't have a collision like that without completely catastrophically smashing up anything that went into the collision. So lots of stuff. The interesting thing about plate tectonics and subduction zones is that you can think of the subduction zone, which is where the plates are moving to as they go down. It's a bit like the plug outlet, on your bathtub. That if you leave all your rubber ducks in the bath and you pull the plug out, they all end up in a little whirlpool in one place, which is where all the water is going down. They pull everything in towards the plug hole, and that's where everything ends up. So that's what subduction zones do. Anything that's on the ocean floor will end up at the subduction zone at some point, and it either goes down or it gets scraped off and goes up. So that's what you see in the Himalayas. You see all kinds of interesting stuff in there.
Yeah.
Because a lot of stuff got scraped off the Indian subcontinent as it crashed in and put up on top. A lot of things that were in the collision have ended up still in the collision somewhere, that you can find little fragments. It's a story of enormous complexity, and any telling of it, you can go down and find some really fascinating little sort of tale that you can talk about in detail.
Yeah.
And the big picture is also fascinating, that you have all these really interesting... I'm also interested in the story you get from the river patterns, that the rivers clearly flow along these sort of geologically historical paths that have got deformed by that collision. They don't just flow down, they flow behind the mountain belt and all the way around. Look at the rivers that end up flowing to the ocean. Yeah. They don't take a nice easy path. They take a long deformed trail, and that's because of this collision. The collision was occurring faster than the rivers could cut their way through, and so they end up being... They tell a part of that story.
Oh, is that really? Wow.
Yeah.
Okay.
So you can look at the map, and you start at the Bay of Bengal and go back, and you realise that the rivers didn't just go up. They don't just trace their way uphill. They go around. There's lots of interesting.
Well, Louis, there's a lot more to talk.
Sure.
Maybe another session down the line. But thank you so much for the chat today.
That's been so much fun.